Welcome to CHEMCASTS episode 2. In this episode we will go over quiz 2, and we'll do it in 3 parts, 1 part for each question. And there are 2 forms for quiz 2, A and B, and they differed only in the numbers used in the questions and the molecules used. So everything we talk about will apply to both forms of the quiz. I'll try to speak in general terms with the strategies that you could apply to both form A and B. So let's get going. The first question that we'll tackle, the question asked, what is the vapor pressure of a solution consisting of mixing 50 grams of one liquid with 50 grams of another liquid, and we're given the vapor pressures of those individual liquids. So the approach that we need to take, the equation we need to use to solve this, is knowing that the vapor pressure of the solution equals the mole fraction of one component multiplied by the vapor pressure of that component plus the mole fraction of the second component multiplied by the vapor pressure of the second component. The next thing that we need to know is what mole fraction is. So mole fraction of component A equals the moles of A divided by the sum of the moles of A plus the moles of B. And we're given that there are 50 grams of each component, so we need to use molar mass to convert grams of one of the components into moles. So 1 mole has some number of grams. So we first figure out the number of moles of A, the number of moles of B, and then we can figure out, say, the mole fraction of A. And then a neat little shortcut is, once we figure out the number of moles of component A, we can use the fact that the mole fraction of A plus the mole fraction of B has to add up to 1. We can use that as a little trick to quickly figure out, say, the mole fraction of B if we already figured out A. Just do 1 minus the value we got for the mole fraction of A. You could do it the normal way, and just the mole fraction of B equals the moles of B divided by this sum. So the key to this problem was knowing this relation, and there's a key assumption that goes into allowing us to use this equation, and that assumption is that this is an ideal solution. And so what we mean by an ideal solution is that when we mix component A and component B together, that the interaction between A and B is about the same as the interaction A had just with itself and the molecules of B had just with itself. And said another way, when we mix component A and component B together, the enthalpy of solution is about 0. And so in practical terms, that means when we mix A and B together, heat is neither absorbed or released. So the solution stays the same temperature. That's a practical way of knowing we have an ideal solution. The so that was the answer to the second part, what assumption was necessary to solve this problem, and said quickly that the solution is an ideal solution. Another thing that we had to know behind the scenes to solve this problem was that component A and component B, the liquids, when we mix them together, that neither of them dissociate. That is, that the Van't Hoff factor for these 2 liquids is both 1. And so we kind of know that the molecules on these problems, we had acetone and propanol in one case, and the other form we had propanol and methanol. And these molecules all have just carbons, hydrogens, and oxygens. And it's a safe bet for these organic molecules, when you put them, when you make a solution out of them, that they don't dissociate. So the Van't Hoff factor is 1. This equation, there's a little bit to it. Just remembering, the vapor pressure of solution equals mole fraction of A plus times the vapor pressure of A, etc. These liquids are volatile liquids, and we know they're volatile because a vapor pressure was listed for them. In some of the problems that you've worked in the book, the solute is non-volatile, and the equation we use when the solute is non-volatile just looks like this half, where we have vapor pressure of solution equals the mole fraction of the solvent times the vapor pressure of the solvent. And so for a non-volatile liquid, or a non-volatile solute, which is usually solid, liquids always have a vapor pressure. For a non-volatile solute, the vapor pressure is 0, and so this whole term goes to 0. So if you're going to remember one thing, remember this full equation, and remember that the vapor pressure of a non-volatile solute, like a solid, is 0, and so that term, 0 times anything is 0, right? So in that case, you would just have the mole fraction of one component times the vapor pressure of that component. So that is the vapor pressure of solution problem, and stay tuned for the other 2 parts.